Hey, welcome to Appendix 3, Collecting Data. We're also going to talk about Appendix 4 in this video. So our objectives for Appendix 3 are to identify ways to survey people. We're going to talk about a biased survey group or an unbiased survey group. We're going to talk about sample size and also something called margin of error. So first of all, let's suppose that I am trying to do an experiment to determine if something's going to happen. One way I could do this is to create a simulation, an experiment that models a real-life situation. And here's an example. A movie theater is giving away a prize card with every ticket purchase. Each card allows the holder to get one of 6 different concession stand items. If you are equally likely to receive each of the cards, how many tickets would you need to buy in order to receive at least one of each prize card? The first question is, how could I do a simulation without actually buying tickets? And we could figure out the probability, because we've learned about that already, but to do a simulation, what I mean is we could use dice. We could draw numbers out of a hat. Or we could use the random number generator on our calculator. These are all ways I could simulate me going to the concession stand or me going to the movie theater a bunch of different times and every time getting a prize card. So could roll dice to have some sort of random way of figuring out how likely am I to get all 6 prize cards within a certain number of dice rolls, something like that. What materials would you need? That depends on the simulation you're doing. Let me give you an example of what I'm talking about. I'm going to use a random number generator on my calculator because that's the one I could show you in a video. I can't really show you rolling dice right now. So let's suppose that I am going to the movie theater. So again, every time you go to the movie theater, you get a different prize card. There are 6 different prize cards total, it said. So I'm going to call those prize cards 1, 2, 3, 4, 5, and 6. And here's what we're going to do. Via my random number generator, I'm going to randomly generate numbers to represent me getting the prize tickets. Here's how I get to my random number generator. You're going to hit the math key on your calculator. So your screen now looks like this. You're going to scroll over to the probability section again, which we are very familiar with after doing chapter 12. And you're going to select number 5, which says rand_int, and that stands for random integer. An integer is a counting number, goes negative and positive. Now when you look at your calculator screen, it now looks like this. Actually, I'm just going to quickly make that higher up so you can see it better. There we go. And now what we need to do is give our calculator a starting possible value and an ending possible value. And for our simulation, we want it to go from 1 through 6. So I'm going to do 1, 6. And if you haven't ever used the comma button before, it's right next to the parentheses. So now my calculator looks like this. And again, this is the smallest possible random number it's going to generate, and 6 then is the largest possible random number it's going to generate. And this, again, I could do this with a dice roll, and that actually maybe would be faster, but here I am with my calculator, so we'll use it. Now, in order to randomly generate numbers, we're just going to hit enter a bunch of times. So hit enter, and it will output a number. So in this case, the random number it generated was 6. So I'm going to put a tally in my chart at 6. This is me right now doing an experiment. So this is me simulating, okay, I went to the movie theater, I got prize card number 6. And now think back to our original question is, how many do I need to buy in order to receive one of each prize card? So we are going to keep going until we have gotten all of the numbers 1 through 6. In order to randomly generate more numbers, just hit enter again. So I got 6 a second time, so another 6, and then I got a 1. And by the way, if you're doing this right now, your calculator is going to output something different, right? Because it's random. Next, I'm getting a 4. So your choice, maybe you want to do this on your own and write down what your calculator is generating, or if you want to write down what mine generated, that's fine too. Okay, next I got a 3. Next I got a 5. We're almost there. Next I got a 1. Next I got a 3. Then I got a 6, and then I got a 2. Okay, so what I just simulated was, this is every single time I got a random number, that was me going to the movie theater, and the number was which prize card I earned. So if I count this all up, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, it took me 10 trips to the movie theater to get all 6 of the numbers. So it took me 10 tries to get all 6 of the prizes. And then here's the deal. Right now, we just did a single experiment, and we could say based on our experiment, the original question was, how many tickets would you need to buy in order to receive at least one of each prize card? We just figured out from our experiment, you need to buy 10. Now, that's not totally accurate though, right? Because every experiment would be slightly different. So, in order to really do a true simulation, we would want to do this experiment several times and then average our results. So let's say if every person in the class did the experiment on their own and then we averaged how many tries it took all of us, then we'd have a more accurate result. I want you to pause right now and write down questions you have about this, because I think it's kind of tricky, so we can talk about anything you want to tomorrow. Just let me know. All right. Another way to collect data is by conducting a survey. So we just did what was called a simulation. A survey is when you actually go out and ask people what they want. There's a bunch of vocab words. I just copied this down, so you might want to just underline the ones that you're going to need to know. A population is a group of people or objects that you want information about. When it's difficult to survey an entire population, we survey a sample of the population. So almost every single survey, it is impossible to survey every single person. For example, political polls, it's impossible to survey every single person who's going to go vote. So they just survey a sample of people. Here's a key concept for this section. An unbiased sample is representative of the population you want information about, and a biased sample overrepresents or underrepresents part of the population. Let me give you an example and it'll make a little more sense. So let's say a survey is being conducted to decide on a yearbook theme. Students can choose from a sports theme or a music theme. Tell whether the given sample is biased or unbiased. All right. We don't know for sure what people are going to want, but we could assume if I was going to survey students on the volleyball team, I'm going to say that's a biased survey. Because they specifically play sports and maybe they're into sports, they may be more likely to pick the sports theme versus the music theme. They may be more likely to pick a sports theme. Now that's kind of making a generalization about people. That's what we do when we're talking about bias, though. They may be more likely to pick a sports theme. Okay, now let's say that I randomly go up to students in line at the cafeteria. It seems random, so probably unbiased. Again, we can't say for sure, but you can assume that as much as possible that's going to be random. Other ways of doing a random, unbiased survey would be picking random numbers from the telephone book, randomly talking to kids as they enter school, randomly talking to kids as they leave school, stuff like that. Now, we're going to talk a little bit about simulations and sample sizes. In a simulation such as the one in example 1, the results are more accurate if you increase the number of times you perform the simulation. I already talked about that a little bit. As the size of a sample increases, the sample will more accurately represent the population. So here's what they're saying. If I was to in a school survey and I only surveyed 5 students, that probably does not represent the entire student body at Delano very well. But if I go back and I survey 500 students, that would probably a lot more likely represent what people at Delano truly feel about something. So the larger the size of the people you survey, the more accurate the results are. And then because a sample is only an approximation, your survey results are not exact. So there's something called a margin of error, margin of sampling error, that indicates how likely you are to get the response that you asked for. And we have a formula for finding this that's on the next page. So flip to the back. So a margin of sampling error for a random sample size of n taken from a large population, the margin of sampling error can be approximated by this formula. All right, so you need to write this down. N in this formula is the number of people that you have surveyed. And S is the sampling error as a decimal, and then you usually convert it to a percentage. Sampling error as a decimal. Here's how we're going to use this. Here's an example. In a survey of 1,600 voters, 51% said they voted for candidate A. What is the margin of sampling error for the survey? So they will always give you some percentage that was hooked with the survey, but in order to find the margin of sampling error, we only use the number of voters. So here's my formula. I'm going to plug in my N, which in this case is 1,600. And this one I can just type up in my calculator. So I can do 1 divided by the square root of 1,600, and I get 0.025. And remember I said S is as a decimal, so if I convert that to a percentage, that is 2.5%. And a margin of error is always above and below, so I'll say plus or minus 2.5%. And then I'll explain in a second. Because here's the deal. In this survey of voters, 51% said they'd vote for a certain candidate. Again, we've only surveyed 1,600 people. We haven't surveyed every single person who's going to vote. So we don't know if 51% is totally accurate. The margin of error tells us, well, I don't know if 51% is correct, but it's probably going to be between, and to find the percentage that's probably going to be between, I take my original percentage, and on the low end, the margin of error tells me it could be as low as, we'll take 51%, subtract 2.5. It could be, the actual amount of people could be as low as 48.5%, or on the high end, add our margin of error, add 2.5. On the high end, it could be as high as 53.5%. So that is the interval. It's likely, and again, we don't know for sure, this isn't totally accurate because it's just a survey, but that interval is likely to contain the exact percentage. So if, let's say, candidate A is really interested in how they're doing in this state or in this town or whatever, they know that probably most likely the lowest percentage they've got here is 48.5%. And the highest percentage they've got is 53.5%. Because we add and subtract it, that's also why I have the plus or minus there. All right, sometimes they're going to actually give you what the margin of error was, and we have to find how many people were surveyed. And this is, it seems strange, but the margin of error is totally dependent on how many people were surveyed, and this is it that they use in the news and everything. So in 2012, we had an election going on. You see all the time all those different polls. At the top of the screen, they have a plus or minus a certain percentage. They're using this formula to find that percentage, and that means margin of error. So start watching for that next time you see surveys on the news. And then here's how I take a margin of error and find out how many people were surveyed. Here's my example for 4. In a school survey, 18% of students named 18% of students named root beer as their favorite soda. The margin of sampling error is 5%. So again, the other information given is just other information. We use the sampling error to find our students surveyed. It's 5%, but S is as a decimal, so I need to change 5% to 0.05, and now I need to solve for N. This might seem a little tricky, but not too bad. Here's what I recommend. Whenever you have your variable on bottom of a fraction, I recommend that you pretend like this side is a number over 1, and then we'll cross multiply. So one of the crosses is 1 times 1. The other cross is 0.05 times the square root of n. Now I can see I want to get rid of that number in front, so I'm going to divide by 0.05. And I get approximately 20, or maybe exactly, I didn't check. And then to get rid of a square root, I'm going to square both sides, and 20 squared is 400. So 400 students were surveyed to make that survey results, 400. All right, next. During the 2012 election, Miss Olson was watching TV and saw this: 48% Obama, 52% Romney. At the top of the screen it said plus or minus 4.2%. Again, this, I actually did see this. This was in the news. They always have this up there, but they don't explain what it is. So now you know next time you're watching this. If you were to explain what the plus or minus 4.2% meant to someone, what would you say? So here's what I would say. I'll explain it and then we'll summarize. I would say surveys of people are not exact measures of what will truly happen. It's impossible to survey everyone. So when we do a survey, we just take a small sample of people. This plus or minus 4.2% represents the error that it may have happened because we sampled such a small amount of people. Every survey is going to be off by a certain amount then, and the more people you survey, the smaller the margin of error. So let's see. I want to summarize that. Let's say surveys are not exact measures and maybe we'll just say more people surveyed equals more accurate. And more accurate means a smaller margin of error. Alright, how many people were surveyed for the poll? So again, I'm going to take my 0.042, convert it to a decimal. I am going to pretend like 0.042 is over 1, and I'm going to cross multiply. So I have 1 equals 0.042 times the square root of n. I'm going to divide by 0.042, and I get approximately 23.81. That's rounded. Leave the real number in your calculator when you square it. And I get approximately 567 people. So this is kind of funny because a reputable news station is giving some survey results on a state, and all it says, they've only surveyed 567 people, but they're using those results to predict what candidate is going to win this state. It's kind of interesting what the news will do sometime. And then let me ask you, can Romney be confident he would win that state based on the poll? Well, to figure this out, it said that Romney was at 52%. So based on our margin of error, let's find what the actual true low end is. And remember, to find the low end, you subtract the margin of error, and to find the high end, you add the margin of error. So on the high end, it could be 56.2%. On the low end, it could be as low as 47.8%. So can Romney be confident he's going to win the state? No. He may lose because it might be as low as 47.8%. We've got one example left, and I'd like you to try it on your own. So remember our formula we were talking about. Please pause the video and try example 6A and B, and then we'll talk about it. Alright, so for example 6A, I got approximately plus or minus 7.07%. And for example B, bringing the margin of error down to 3%. So I put 0.03 in for S and solved it using the process I did in example 5. And I got 1,111 people. Alright, thanks for watching. Please open up your Appendix 4 notes now. In case you're feeling panicked because this video is already at 20 minutes and you're like, oh no, we have a whole nother worksheet. Appendix 4 is going to be a lot faster because it's about bar graphs and pie charts, and we do not need to spend as much time on it because you guys know this from your past. So our purpose with example 4 is to look at graphs, to interpret data from graphs, and then also to identify something called misleading graphs. So just a quick review from middle school. We've got different ways that you can graph data. So there's circle graph, histogram and bar graph, line graph, box and whisker plot, stem and leaf plot. There's a reason why we would use any of those data displays. So here I have a list saying why each display is worthy. So for example, circle graph shows data as parts of a whole, so you could see what percentage of the total your thing is. Histogram or bar graph just shows the data in different categories so you can compare it visually. A line graph shows data that changes over time. A box and whisker plot, we already talked about that in section 7.7. That shows a spread of data. And stem and leaf plot also shows a spread of data. I've got a few examples here. Example 1, we've got some area of the different 5 Great Lakes. And then it says to create a data display comparing the area of Lake Superior and area of Lake Erie. And the book already did this for you. So here are my graphs and charts. And the question is, why are each of these displays the correct way to display this data? Why would I want to use both of these? So there's lots of different correct answers for this, okay? But this is just something I'm coming up with. If I look at a bar graph, it lets me visually see how each thing is different. So for example, in this bar graph, I'm able to right away look at it and see that Lake Superior is 3 times the size of Lake Ontario. And I'm able to see that Huron and Michigan are pretty equal. And I'm able to see that if I added together Erie and Ontario, it wouldn't even match up to Superior. Now look at the pie chart. The pie chart, remember, shows us a percentage of a whole. So I'm able to see if I took the whole area of all of the Great Lakes together, Lake Superior is still the biggest, but as a percent of the whole, now it doesn't look quite as big as the others. I'm going to say it shows a visual of percent of the whole. And we can kind of see, looking at this, Lake Huron and Lake Michigan are about half of the total. And I can make other conclusions too. I mean, this graph makes it look like Lake Ontario and Lake Erie are very close to each other. Lake Superior is obviously still the biggest. Flip to the back when you're done looking at that. Maybe come up with your own idea of why it would be cool to use either one of those graphs. All right, on the back side, we want to talk about something called misleading graphs. So one thing that you'll often see in the news, actually, sometimes it's even very entertaining, they'll draw a graph in a way that basically people want to make graphs and charts to emphasize a point they're trying to prove. So if you're trying to prove that something increased a lot over a certain time period, you're going to create your graph so it looks like it increased a lot over a certain time period. Here's what you want to watch for. I want to watch for broken scales, collapsed data categories, scale dimension of objects. And sometimes they just straight up leave some stuff out. So here I have a list of different types of music. If I look at music store sales, I got R&B, pop, rap, and rock. But you know what? This chart totally fails to show that actually country music is 16% of music store sales, which is actually higher than pop and R&B. They just threw it in the other category. This may have been someone, I mean, if you think about who was creating this graph, probably someone who wanted to emphasize that rock, rap, pop, and R&B are the categories people like. Someone who didn't like country for some reason. So country is 16%. It's actually more than pop and R&B, but it was thrown in the other category. When you're looking for misleading graphs, there's not a specific thing I can tell you to use every time, because every graph is going to be slightly different. So look at the graph, think about how the scale is, think about how they displayed the data, be creative in your thinking. Let's look at B. Alright, now look at what's going on here. This graph makes it look like there was a huge decrease between 1970 and 1980, but it's actually only a decrease of 6,000 people, which is very small considering that the total population is 104,000. So losing 6,000 people actually isn't that big. Because they made this broken scale right here, they made it look like it was a big decrease. So if I was going to write my answer to this, maybe I would say there is only a decrease of 6%, but the broken scale on the graph makes it look like a really big drop. And it is correct to use a break in a graph. I mean, it's okay to do a break in the graph. The problem comes if this was a news station that was saying, oh, the population decreased so much between 1970 and 1980. The problem comes in if you're trying to prove a point using a graph that looks a certain way. Alright, moving right along. So the rest of the lesson today we've talked about a little bit, but there's just one new thing that I want to add, and that is when you take an outlier out of a data set, how it affects the mean, median, mode, standard deviation, and so on. So this is a continuation of what we learned in section 7.7. I'm going to do the same sort of stuff I did in section 7.7, but we're going to calculate this data once without the outlier and once with the outlier and see what happens. So I got a city's temperatures in degrees Fahrenheit during a 14-day period. I'm going to use my calculator again to determine this data. So go ahead and pause, plug it in and try, or if you want to just let me do it for you, when you unpause I'll have it up there. Alright, I got a median of 32.5 from my calculator output. I got a mean of 33. I have a range of 7. My standard deviation was 2.20. And my mode I found by hand, and I found it to be 32. There's more 32s than something else. Okay, here's what we're saying. For example, B. On the 15th day, the temperature was 49 degrees. Calculate the new mean, median, mode, range, and standard deviation. Okay, to save you some time, what I did is I just took my calculator, I put 49 in there also, and then I recalculated all this stuff. And I'll just give it to you right now, okay? So the mean with that new value in there is now 34.1. The median is now 33. The mode was still 32 that I just calculated by hand. The range is now 19, and the standard deviation is 4.5. Next question of the mean, median, and mode, which measure of central tendency is affected the most? And which one's affected the least? Okay, so affected the most, the range, the standard deviation, greatly increased, and the least, the median and mode. And like I said the other day, because the median mode are the least affected by outliers, often the median will be used when talking about things such as household income or household value. Question, what effect does an outlier have on the range and standard deviation? Well, it increases it. An outlier makes the data more spread out. Outlier makes the data more spread out. All right, that's all I got for you today. Thanks for listening and have a great night.